Okay, another small video on the final assignment on matrices. This is page 3. I think we can do this pretty fast. Yeah. So you were given 5 matrices, or you were given sort of 5 problems in which a geometric linear transformation was described to you, and what you had to do was come up with the matrix which performs that transformation. Okay, let's go. I'm going to assume people are pretty good at this, so okay, well, we begin. A says, rotate point by 90 degrees counterclockwise. Alright, so I'm not sure I don't really have enough room here, I realized, but anyway, maybe this is not that hard. Maybe I'll sort of do some scratch work or something down here, even though that's a terrible idea. Oh man, should I maybe just, here, I'll do B down here, or something. So I want to rotate points 90 degrees counterclockwise. Well, okay, maybe the first thing to do is just to draw a picture and recognize that what I want is to figure out what happens to the unit vector 1, 0 and the unit vector 0, 1. And okay, well, what does happen if you rotate 90 degrees counterclockwise? We've done this problem so many times, but everything kind of goes like this, right? So 1, 0 gets sent here to 0, 1, and 0, 1 gets sent here to negative 1, 0. And so the matrix basis theorem tells you that the matrix which performs this transformation is the matrix with certain columns. And the first column of the matrix, which rotates points 90 degrees counterclockwise, is what that matrix is supposed to, or what that transformation does to 1, 0. And we've seen that 1, 0 goes to 0, 1, and so the column is 0, 1. And the second column of any matrix is what that transformation does to 0, 1, and 0, 1 gets sent to negative 1, 0, and so sort of that's just kind of it. Okay, so maybe down here or something, I will do B, because I erased it. This is sort of dilate by scale factor 3. Okay, well, maybe this one is sort of too easy or something. Here's 1 and negative 1, and you can even draw in the box if you like. Well, what happens? 1, 0 gets sent to 3, 0, and 0, 1 gets sent to 0, 3, and you end up with this rectangle square which has been dilated by scale factor 3. And so I think this one is easy because we've done it so many times. The first column is what a dilation by scale factor 3 is supposed to do to 1, 0. It's going to send it to 3, 0. And what does it do to 0, 1? And sends it to 0, 3. Okay, so good. Sort of 2 down. How about C? What happens if we are going to reflect across the line y equals x? Well, once again, I can just, well, these just interchange now, right? 1, 0 goes to 0, 1, 0, 1 goes to 1, 0. So that's just kind of it. That is the line y equals x. And so what is the matrix which will perform this transformation? It will send 1, 0 to 0, 1, and it will send 0, 1 to 1, 0. Okay, those are just kind of warm-up because I guess we've done them so many times. Maybe D is also not so hard because we have also done it before, but let's sort of do it again. And here you're going to see that this is sort of an example of, in my opinion, how the language should be, how we should sort of describe this vertical shear. What does it say? This is my sort of phrasing. I want a vertical shear that moves the y-coordinate by an amount 3 times the x-coordinate. Okay, so in this case, I think definitely we should draw in 1, 0 and 0, 1. And that's 1, 0 and that's 0, 1. And if I can tell what this matrix does to those 2 unit vectors, then I'll be done. Okay. Well, it's a vertical shear. It moves the y coordinate. by an amount 3 times the x-coordinate. So here, this point 1, 0, its x-coordinate is 1. And so if its x-coordinate is 1, 3 times the x-coordinate would be 3. And so this is going to move the y-coordinate of this point, how much? By an amount 3 times the x-coordinate. In other words, this thing is going to move up 3. And this point now is, instead of 1, 0, 1, 3. Because the y-coordinate got increased by an amount 3 times the x-coordinate. But here, since the x-coordinate is 0, this doesn't get changed at all, so 0, 1 goes to 0, 1. And if you want to draw in the parallelogram, there it is, and indeed this is a vertical shear. Okay, so the matrix that will do this sends 1, 0 to 1, 3, and just sends 0, 1 to 0, 1. Alright, so this was all review. We did problems like this, exactly like this in class. Okay, maybe this was the first one now that was a little bit of a challenge. E, how do you rotate points 150 degrees counterclockwise? Now, we did a little lesson via video on using a matrix which will rotate by theta degrees counterclockwise. So you could go sort of find that in your notes and then sort of try to convert, okay, 150 degrees clockwise, well, what does that mean? That's like 210 degrees counterclockwise, you know, blah, blah, blah. But I really think that's kind of not in the spirit of things. I think more in the spirit of things is to just draw a picture, just do it from scratch. So, by that I mean, let's just draw in 1, 0. So there it is, 1, 0. And let's draw in 0, 1. So there it is. And now, okay, so there's some kind of, well, maybe I'll do this in black. So there's some kind of circle about which, because we're rotating, there's some kind of a circle that we're kind of rotating around, and that looks kind of like this. And now let me just draw a picture of what happens when I go 150 degrees clockwise. Well, 150 degrees is like, 30 less than 180 degrees, but I'm going clockwise now, so it's going to be going like this, like a clock. And so the bottom line is I'm just going to end up here. I'm going to end up here at this point. I guess I shouldn't use purple. I'll use red because that's what I've been doing. This point is simply what you get when you rotate this vector 1, 0 by 150 degrees clockwise. And okay, what is that point? Well, it's just kind of like 7 pi over 6 basically, right? So it has coordinates negative root 3 over 2, comma, negative a half. Just like fact of the unit circle, geometry, whatever you want to call it. Okay, and well, next, what happens when 0, 1 gets rotated 150 degrees clockwise? Well, it's going to go, not quite 180 degrees, so it's going to end up here. Why? Because, well, that's just 150 degrees, just from there. Okay, and what's that point? Well, once again, I just know from knowing my unit circle, right? So that's more or less 5 pi over 3. So that's 1/2 comma negative root 3 over 2. And so, not even using any really trigonometry per se, or any kind of memorized facts, but just sort of doing it from scratch, this whole thing gets kind of rotated. So so this is like a right angle, and then this is a right angle. So then we're done, because the answer to the problem is, well, what does this matrix do to 1, 0? It sends it to negative root 3 over 2, negative a half. And what does this matrix do to 0, 1? It sends it to 1/2, negative root 3 over 2. Okay, good. And then the final thing, and these directions might have been a little bit vague, I said something like, write the matrix ACE and describe in words the effect. Okay, well, the big sort of important thing that we learned last week was that if you take a matrix A, and you take a matrix C, and you take a matrix E, and you multiply them all together, then what you're really doing is creating a new matrix. Well, anytime you multiply two matrices, you're creating a new matrix, which is the composition of the two functions encoded by those matrices individually. And so, all I really wanted you to say here, all I really wanted you to sort of appreciate and understand, is that if I have some kind of vector, xy, what is matrix ACE ultimately? The product of these three matrices does the same thing as if you were to sort of line the matrices up like this. But when you line the matrices up like this, you see that first an arbitrary vector is getting plugged into matrix E. And when this arbitrary vector gets plugged into matrix E, only then does the output get plugged into matrix C, because matrices are functions. And only then that output goes into A. And so the answer is, when I said describe it in words, I'm just going to say it out loud. What does this matrix ACE actually do? It takes a vector, it first performs the E operation. In other words, it takes a vector, rotates it 150 degrees clockwise. Then the result is being plugged into matrix C, so then it reflects about the line y equals x, and then the output goes into matrix A and gets rotated 90 degrees counterclockwise. So the final sentence is, what does ACE do? It first rotates 150 degrees counterclockwise, then reflects about the line y equals x, and then gets rotated by 90 degrees counterclockwise. And then the final thing I wanted you to do is just do the multiplication. So let's just do that. This is A, assuming I did all of this right. C is this one, and E is this one over here, negative root 3 over 2. So now basically just crank out this multiplication, please, just to prove to me that you know how to do it. I think the easiest way would be to multiply A and C first. It doesn't matter because matrix multiplication is associative. Yeah. Okay. So here, let's see, row 1, column 1, so that's negative 1. Row 1, column 2 gives me 0. Row 2, column 1 gives me also 0. And row 2, column 2 gives me 1. Let me just double check that. Chop chop, that's probably right. Whew. Yeah, sure. Okay, and then I'll multiply these. So yeah, let's see. Row 1, column 1 gives me just root 3 over 2. Row 1, column 2 gives me negative a half. Row 2 times column 1 gives me negative a half. And here I get row 2 times column 1, negative root 3 over 2. So hopefully this matrix will do that. I guess we could just check it or something. Or I don't know if that's a good idea. Take 1, 0, and first rotate it 150 degrees counterclockwise, boom. Then reflect it over the line y equals x. Oh man, that's already sort of too hard for me. It will end up here, negative a half, negative root 3 over 2, and then 90 degrees counterclockwise would take me here. So that looks right, that one looks right, just checking based on using my wits. And, well, alright, I've already started this process. So now, if I take 0, 1 and rotate it, first perform matrix E, it will end up here. Then I want to reflect across the line y equals x. So that's going to go here to negative a half root 3 over, no, sorry, I zoned out for a second. 100 negative 3 1 half. I guess it's going to end up here. Yeah. Yikes. What? Sorry, I lost my train of thought for a second. Negative root 3 over 1. Yeah, it's going to be here. Yeah. and then, because it's like 1645, yeah. So then, finally, 90 degrees counterclockwise will take me here, and so again, I'm right. Okay, so I just kind of double checked that this matrix, this product matrix, really does do what I thought it was going to do. So okay, that's that page.